Today, I decided to go back over the difference between a PWM solar charge controller and an MPPT, but this time with 4 simple case studies. First with a single solar panel, then with multiple solar panels to better understand the impacts. And once again, there will be a wiring diagram for each of the examples. We will compare the energy production of each setup using a PWM controller versus an MPPT. I will also give you the main disadvantages and advantages of choosing one over the other. And before that, I will briefly explain how these two devices work. But before we start, you will find in the first link below the video our electrical diagram pack in the description. Also, don't forget to subscribe to the channel, drop a like, and feel free to ask your questions in the comments. Alright, let's quickly start by looking at what a PWM is. It is a type of charge controller used in solar systems, as you can imagine, but not only in that context. In the case of solar energy, it adjusts the width of electrical pulses to control the amount of energy sent to the battery. To put it simply, when the solar panel produces energy, the PWM controller acts like a fast switch that opens and closes several times per second. The more the battery is charged, the shorter the pulses become, thus reducing the incoming energy flow. For example, here the average voltage is 12 volts. To reduce the voltage, we act on the duty cycle. At 50%, the average voltage becomes 6 volts. Another example, if we have a solar panel of 18 volts, a duty cycle of 75% will allow for a charging voltage of 13.5 volts for the battery. We will see later on, but with this type of device, we cannot control the current. The MPPT, on the other hand, is an advanced type of solar charge controller. Unlike the PWM, it is capable of converting the excess voltage produced by the panels into additional current, thus increasing the overall efficiency of the system. For example, if a solar panel produces 18 volts and the battery is at 13.7 volts charging voltage, the MPPT will convert the excess voltage into additional current. This way, almost all of the power generated by the panel is used. But now, let's move on to the case studies to understand it better. Here is a wiring diagram with a 175 watt solar panel connected to a PWM charge controller and linked to a 12 volt battery. As for the solar panel, its optimal operating voltage is 18.1 volts and its current is 9.67 amperes. This gives us 175 watts when we multiply the voltage by the current. Here, since the PWM will be connected to a 12 volt battery and the charging voltage will be around 13.7 volts, it will adjust the voltage it receives at the input. The problem is that the PWM will have no effect on the current. As a result, the actual power transferred will be 13.7 volts times 9.67 amperes, which is approximately 132.5 watts. So there is a potential energy loss. 175 watts minus 132.5 watts equals 42.5 watts lost, which is about 24% loss. Now let's directly compare this simple setup using an MPPT controller while keeping the same solar panel. For the battery, we can stick with a gel lead acid battery, but more importantly, we can switch to a lithium battery, which is not recommended with a PWM controller. The special feature of the MPPT is that it optimizes power conversion by adjusting both the current and the voltage to maximize the recovered energy. It therefore converts the excess voltage into additional current to improve efficiency. The theoretical maximum power will be, as in the previous setup, 175 watts. The MPPT will adjust the current to match the voltage and technology of the battery. Since the MPPT retains almost all the power, we will assume here an efficiency of 97%. So the transferred power is approximately 175 watts times 0.97, which equals around 170 watts. So if we compare the two controllers, the actual power will be 132.5 watts versus 170 watts for the MPPT. This gives a daily production over 5 hours of sunlight of 662 watt hours versus 850 watt hours. That means a much higher charging capacity and a loss of less than 5% with the MPPT compared to the panel's theoretical power. And you will see that the next two cases are even more interesting. Now let's try to make the most of this PWM controller, which has a maximum charging current of 30 amperes. We can connect several panels to it. But here, there is one limitation. The panels can only be connected in parallel. Why do you think that is? Because the PWM works better with panels wired in parallel, as it does not convert the voltage. In parallel, the voltage remains the same at 18.1 volts, and the current adds up. So here, we can connect a maximum of 3 panels to stay within the controller's limit. Each panel produces about 9.67 amperes, which gives us just under 30 amperes. The theoretical power is 3 times 175, which equals 525 watts. But with the PWM, the voltage is limited to that of the battery, around 13.7 volts. The actual transferred power will therefore be 13.7 volts times 29 amperes, which is approximately 397 watts. In conclusion, you can connect 3 175 watt panels in parallel to reach about 400 watts of real output. With this PWM configuration, you lose around 24.4% of the panel's theoretical power. This is due to the PWM's inability to convert the excess voltage into usable current. Now let's compare the setup with these same 3 panels, but this time using an MPPT controller. Here, the wiring is very different since we will connect everything in series. This gives us a voltage of 18.1 volts times 3, which equals 54.3 volts. In series, the big advantage is that the current remains the same, that is 9.67 amperes. And the total theoretical power, 175 watts times 3 equals 525 watts, no change here. The MPPT converts this higher voltage into usable current for the battery. So, assuming an efficiency of 97%, we are looking at around 509 watts out of a theoretical 525. What is interesting is, first of all, to compare the performance values of the 2 controllers. As you can see, an MPPT delivers much better performance because it allows the full power of the solar panels to be used. Of course, one could point out the price difference between the PWM and the MPPT. However, in some specific cases, the MPPT still ends up being cheaper overall for the entire installation. The need for parallel connection to match the battery voltage increases the current intensity. As a result, the high current in parallel causes more loss over long distances, requiring thick and expensive cables. Furthermore, a PWM does not adapt to changes in sunlight. In low light conditions, the efficiency drops more compared to an MPPT. The PWM charges the battery more slowly and less efficiently, which can lengthen the daily recharge time. In summary, the PWM is simple and affordable, but it significantly limits the system's efficiency and scalability. Therefore, an MPPT controller is better suited to maximize production and optimize charging, especially when using multiple panels.